All right, good morning, CCTI pre-calc students. Mr. Bashar here once again. Into a new chapter, into a new topic, trigonometry. So you guys have been exposed to trig for about a week now on Khan Academy. I hope that you've enjoyed watching the videos and learning a little bit that way. I thought it'd be best, try something different, have you guys learn a little bit on your own first, and then I'll go backwards and kind of reiterate some stuff to you. So the first lessons that you did on Khan Academy for trig was the right triangle trig, right? Which is learning about how to do trigonometry in a right triangle and learning the different ratios, sine, cosine, tangent, etc. Learning how to solve a right triangle. So today I'm going to review a couple of those things. This is going to be one of a few videos. So the first video today kind of reflects on stuff that you learned last week, and it goes a little bit deeper as you learn about some identities. I'm going to have that mixed in today. And later today, after dinner time, I suppose, I'm going to shoot some more videos on the next part. So you're going to be talking about the unit circle on your next assignment that's due next Tuesday. So I'm not going to do the unit circle. However, I'm going to do stuff on angles and reference angles and quadrantal angles, and take that kind of an angle with the nice little pun, right? I'm going to take that angle to get you up to speed on some of that stuff. And then, of course, we'll later talk about the unit circle. But, you know, just try this new type of learning for now. Watch the videos. You've been doing a good job overall. I can't complain. But today I'm going to go over in this first video some stuff that you should have learned. So a good place to start if we want to look at right triangle trigonometry. What exactly is trigonometry? Well, it comes from the Greek word trigonometria, which means measurement of triangles. So essentially, trig was based on the idea of measuring triangles and finding information about triangles that specifically algebra couldn't solve or geometry couldn't solve. So we're going to learn about solving right triangles, and we're going to start off by looking at a right triangle here. And I'm going to draw it in this fashion. Now, as you've seen, we can orient the triangle any way we wish. So I'm going to start off by drawing this right triangle and putting an angle here. This is the angle theta. So in trig, usually we use theta. Theta means an angle. And remember, after all, trig functions are functions like any other function. They're just represented a little bit differently. And we don't quite see it here in the right triangle. But think of it this way. You remember your function machine, right? 50 cents goes in, you get your Coke out. Well, it's the same way with trig functions. What goes in is an angle measure. So you plug in an angle into the trig function and you get out a real number. And you're going to see that with the unit circle specifically as we go forward. So if we have a triangle like this, and we have an angle theta right here, we can label this triangle as a few things. As you know, the long side is called the hypotenuse. This is across from here is what we call the opposite side. And down here, this is what we call the adjacent side. So you have the hypotenuse is always the long side. Opposite the angle in question is the opposite side. And right next to that angle is what we call the adjacent side. Trigonometry is fundamentally based on two major trig functions, and we can derive everything else from them essentially. So we're going to look at sine and cosine. These are the main two. And we also have tangent. And then from these three we get the reciprocals, which would be cosecant, secant, and cotangent, respectively. Okay? So, in this diagram, if we want to talk about finding the sine of theta would be given as what we call the opposite over the hypotenuse. So for now, that's how we're going to define this ratio. Sine's ratio is the opposite over the hypotenuse. Cosine's ratio is going to be adjacent over the hypotenuse. And tangent ratio is going to be opposite over adjacent. Now, interestingly enough, as we're going to learn, tangent is the slope function. So you could think of this as your y and this is your x. And isn't slope change in y over change of x? There's no coincidences here. It's kind of interesting that way. Okay, now cosecant is the reciprocal of sine. So that's CSC theta, that's the hypotenuse over the opposite, so it's the reciprocal. Secant of theta is going to be the hypotenuse over the adjacent side, and cotangent of theta is going to be the adjacent over the opposite side. So those are the ratios based on sine, cosine, and tangent, and then their reciprocals. Okay, so that's important. We can also rewrite all these trig functions in terms of the reciprocals as we've done here. So for example, sine of theta, we can write as 1 over cosecant of theta. Or we could also say that 1 over sine theta is the same as cosecant theta. Cosine theta is 1 over secant of theta. So sine is 1 over cosecant. This looks kind of messy here. CSC theta. So cosine theta is 1 over secant of theta. And we could also say that 1 over cosine theta is secant theta. And tangent of theta is 1 over cotangent of theta. And we could also say that cotangent, we could say 1 over tangent of theta is cotangent of theta. So these are what we call the reciprocal rules, and they'll be used more frequently when we go a little bit further. But I just wanted to put them out there for you. Okay? So what we're going to do is put into practice our definitions here in a real problem. So I'm going to use this same triangle here. I'm just going to erase this stuff. And we're going to look at actually a special right triangle we have. It's called a 3, 4, 5. A 3, 4, 5 right triangle. Okay, so 3, 4, 5. We want to figure out what these ratios are. So in this one, sine of theta, remember, is the opposite over the hypotenuse. So opposite over hypotenuse, so sine of theta is 4/5. If you want cosine of theta is the adjacent side over the hypotenuse. So adjacent over hypotenuse, that would be 3 over 5. And then tangent of theta is the opposite over adjacent. So opposite over adjacent is 4/3. And if you could always get these three, the other three trig functions essentially come for free because they're just the reciprocals of these guys. So for example, cosecant of theta would be 5/4. Secant of theta would be 5/3. And cotangent of theta would be 3/4. So you get them quite easily based on the reciprocal definitions. Okay? So I don't think that's too bad. That's probably what you saw in Khan Academy from the beginning. Now, a good question we could ask ourselves is this. The definition suggests that sine, cosine, and tangent are functions of the angle theta, which is the lengths, which would mean that the lengths of these sides would be kind of irrelevant for us. Is that true? And the answer is yes. It doesn't matter how big the sides are. What matters is the angle measure itself, because the trig function is based solely on the definition of that angle, right? We have this idea of similar triangles you learn from geometry, in the fact that you could have a small triangle like this and a big triangle like that. but as long as their sides are in proportion to each other, then they are what we call similar. And we kind of think about this idea here in trig. Let me give you an example. There's two special triangles that you should have learned about. The one that I'm going to look at here is the 30, 60, 90 triangle. There's 30 degrees, there's 60, that's 90. Okay, so we're going to look at this triangle first. Now this has special sides. So in the 30, 60, 90, you have across from the 30 is 1, the long side is 2, and across from the 60 is the square root of 3. So those are the measurements in this type of triangle, the 30, 60, 90. Now, if I draw a bigger triangle, let's say I'm inflating everything by 2. So this will be a 4, this would be a 2 root 3, and this would be a 2. So all I did here, I didn't change the angles. The angles stayed the same. But what I did was I enlarged the sides. So I think of it like I stretched it, right? I'll show you that how the trig is only based solely on the degree mark and not on the side, the lengths of the sides. For example, let's look at this guy here, sine of 30, right? So sine of 30 degrees, if you remember your ratio, that is the opposite over the hypotenuse, which is 1/2. Okay? Now, let's compare that to sine of 30 in this triangle. So sine of 30 is going to be 2 over 4. Well, what is 2 over 4? 2 over 4 is 1/2. So you see the sides match, the ratio matches. How about we look at over here cosine of 30? So cosine of 30, that's the adjacent over the hypotenuse. So that is root 3 over 2. Let's look at cosine of 30 over in this triangle. Cosine of 30, that's 2 root 3 over 4. Well, if you reduce this ratio, that's going to be root 3 over 2. So you see, it doesn't matter how big the triangle is, it matters about the angle. So angle measure matters the most. You can almost say the sides are pretty much irrelevant because it all comes down to, with the trigonometry, this angle. We could also look at the 60-degree mark and also do the trig from the 60-degree mark. So for example, if we start back here with the small triangle, let's erase all this stuff. If we look at the smaller triangle, say we want to figure out the sine of 60 degrees. Sine of 60 degrees. Remember what sine is? It's the opposite over the hypotenuse. So that's going to be root 3 over 2. How about cosine of 60 degrees? Well, cosine of 60 degrees, that's going to be the adjacent over the hypotenuse, right? Adjacent, so here's the adjacent side over the hypotenuse, which is 1/2. We could play the same game over here. If we want sine of 60 degrees from this one, that's the opposite over hypotenuse. Opposite over hypotenuse, and that reduces to root 3 over 2. And how about cosine of 60 degrees? Well, cosine of 60, adjacent over hypotenuse, 2/4, which reduces to 1/2. Okay? So that goes to show you how the trig ratios work. Now this brings us to another excellent point, people. The fact that we have two special triangles. We have a 30, 60, 90 that we have to understand the sides on, right? And that's something that needs to be memorized. And eventually you're going to memorize sine, cosine, and tangent for 30, 60, 90, 45, 45, 90. And that's a good place we're going to start. For example, sine of 90 degrees is an interesting one. Sine of 90 degrees is going to be 1. Because here's your 90 degrees, right? So we want opposite over hypotenuse. Well, guess what? Opposite the right angle is 2. The hypotenuse is 2, so 2 over 2 is going to be 1. So that's what happens there. An interesting question to ask is, what is the tangent of 90 degrees? What is tangent of 90? What is that going to be? Well, that's something that you could certainly think about. We could think about this for cotangent. We could think about this for all of them. But these are some interesting angles. Tangent of 90 degrees or tangent of 0. How about sine of 0? Those are all interesting things that we have to consider upcoming. So that's just getting a little bit ahead of ourselves right now, of course. But eventually we all will come to understand what the special angles are in general, 30, 60, 90. So the other special triangle we have to consider is what we call the 45, 45, 90 triangle. That's a bad triangle. This one's a little bit peculiar to draw because of how it looks. So this is a 45, 45, 90. So that would be considered a right isosceles triangle, right? So in this scheme, the legs are worth 1 and the long side is worth root 2. So, for example, sine of 45 degrees, right? You could pick any of these 45s. It's the opposite over the hypotenuse, 1 over root 2. Now, this brings us to an interesting point. 1 over root 2, right? Some books leave it like this, but some books rationalize it. We got to get in the habit of rationalizing. Whenever you have a root on the bottom, we have to get rid of it. We talked about this earlier in the year, if you remember. What we do is we multiply the top and bottom by the root. So we're going to get root 2 over 2. So sine of 45 degrees is root 2 over 2. How about cosine of 45 degrees? Well, cosine of 45 degrees is adjacent over the hypotenuse. So we just have adjacent over the hypotenuse, right? So this is your hypotenuse. This is root 2 over 2, just like the other one. Okay? Let's see what else we have here. How about tangent of 45 degrees? What would tangent of 45 degrees be? Well, tangent is the opposite over adjacent. So opposite over adjacent, that's just going to be 1. So the tangent of 45 is 1. So you're starting to see already some of these special degree marks. And then the lesson you're going to learn coming up is how we extend from beyond quadrant 1. So if we want to form a triangle over here, how is that going to be different? If we want to form a triangle down here or down here, how it changes with these ratios. It's all a sine game and a reference angle game, but that's for another day, another lecture. All right, so let's look at some other examples here, what we can do. So you want to commit these two triangles to memory. So let's see, what else do we want to talk about here? Okay, how about solving a triangle? We want to be able to do that. Let's see. Okay, here's some good examples. I also want to talk a little bit about identities as well. We'll talk about that at the end of this. At the end of this video, we'll talk about a very useful identity we have for helping us find these ratios. But here's an example, and this is an easy one to start off with. Say we have a triangle ABC, we have it labeled this way, and we know that this side is 8, this side is 6, and we don't know over here. Well, this is a very fortunate problem for us because this is a classic Pythagoras, right? So this is going to be a squared plus b squared is c squared. So this would be your b, this would be your c, and this would be your a. So you got 6 squared plus 8 squared equals c squared. This is a very direct problem. You don't need trigonometry for this. 36 and 64. That gives you 100. 100 equals c squared. We'll take the square root of both sides, so that gives you 10. So this side is 10. So this is a 6, 8, 10 triangle. We're very fortunate to have one like this, right? This is no trig required, just the Pythagorean theorem. Pythagorean theorem only works, in fact, for a right triangle. Now, let's look at another example where it's a little more difficult, and we may have to use our calculator. Okay, so we're going to say this is 40 degrees here. That's 50 degrees. And we're given, let's see, this is 3, this is x, and this is y. And we want to find the remaining sides of the triangle, okay? So we can't use Pythagoras here. We know all 3 of the angle measures, but that doesn't really help us quite yet. If we had 2 of the 3 sides, we could use the Pythagorean theorem, but we don't. We only have 1. So we have to use our trig definitions of those ratios to bail us out. So you have a couple options here. You can start here at the 40 degrees and ask, okay, which of these trig ratios is going to help me out? For example, if I pick sine is the opposite over the hypotenuse, so we could possibly use that definition. Or about cosine. We could do cosine of 40 is x over 3. So one of those will be good enough to get us started. The one I did here was sine. So if we look at sine of 40 degrees, based on the way the schematic of this triangle is, that's sine of 40 equals y over 3. You see that? Opposite over hypotenuse. We have to solve this thing for y. So when we solve this for y, we're going to have to use our calculator to help you. Making sure your calculator is in degree mode. Later on, your calculator is going to have to be in radian mode. So this is an easy one. We'll just cross multiply. 3 times sine of 40 degrees is y. So in your calculator, you're going to do sine of 40 degrees and multiply by 3. And you should get something like this. Y is 1.9. Somewhere in that neighborhood. And that's good. We like that. So that's what this is. 1.9. Now there's a few ways you can proceed from here. You now have two sides, so you can actually use the Pythagorean theorem and actually do 1.9 squared plus x squared equals 3 squared, or you can continue to use the trig. Let's look at the trig aspect. If we use cosine of 40 degrees, that ratio is going to get us this x, because remember, cosine of 40, here's the degree, it's the adjacent over the hypotenuse. So adjacent over hypotenuse, x over 3. So once again, we'll say 3 times cosine of 40 degrees is x. We'll use our calculator, cosine of 40 times 3, that's going to give us 2.3. So now we use just all trig to figure out x and y. Okay? So this might be a good place to pause the video to go back and look and see if you could go ahead and figure out the rest of it on your own. Okay, now let me show you another type of problem, one that is a little bit different, where we have to use actually an inverse function to do it. So say we have a triangle. Let's see, we'll call this theta here. This will be a 2. This is 7. And we'll call this x. And what we want to do is find the missing angles. So this time we don't care about the sides. It'd be easy to find the third side, right? Because it's just old Pythagoras. But we want to use the trig because we have to figure out these two angles. So how can we do it? Well, we want to see if we could find the right trig function that will get us somewhere based on these things here. So notice that if we look at the cosine of theta, the cosine of theta's definition is the adjacent over the hypotenuse. So cosine of theta would be 2/7. That's the easiest one to do here, okay? And again, a lot of you may ask, how the hell do you know which trig function to pick? Well, it just takes a little bit of practice. The more it is you do, you'll see right away which one you want to use. So cosine of theta is 2/7. How do we find theta? This is like an inverse function problem, right? Because what we're saying here is cosine of what angle is going to spit out 2/7. In other words, when we put some kind of angle into the function machine, we're getting the value of 2/7 out. So the way that we figure this out using the calculator is we're going to say cosine inverse of 2/7. So you're going to enter that in your calculator, cosine inverse of 2/7, and that's going to give us this value here, about 73.4 degrees. And usually this is going to be some kind of irrational number based on the type of size that we have. Okay? Unless we get lucky and we're working with a 30, 60, 90 triangle where we know some of those values a little more readily, or the 45, 45, 90. But anyway, in that case, you're still getting irrational things like √2, √3. So cosine inverse of 2/7 is 73.4. So what that means is theta is 73.4 degrees. So from this point, you have an option to continue to use the trig or use basic information about a triangle. What you should know from Mr. Anderson is that in any triangle, the angle degrees add up to 180. So what that means is, if we know we have a 73.4 degree angle and a 90 degree angle, and we add x to it, that has to add up to be 180 degrees, right? So we can do a little bit of algebra here to figure it out, or you can just use arithmetic actually, but the algebra is a little more fancier, right? So if you do this type of thing, you're going to get x is 16.6 degrees. Okay, x is 16.6. So now we have the whole triangle solved and figured out in terms of the angles. So that's how you would handle a problem like that. One more comment I want to make here before we exit from this video is that you may have seen this in your last videos that you watched for Khan Academy, is that we have this thing called the Pythagorean identity. And this is a big deal in trigonometry. And it also comes up huge like in calc when you're doing problems. Sine squared theta plus cosine squared theta equals 1. This is what we call the Pythagorean identity. And this will get you out of the jam a lot of times in trig. Okay, it's a very fundamental identity. And where does it come from? Well, it just comes from the fact of using the sides of the triangle and the ratios. For example, if we go back to the right triangle, we know that's just there's angle theta, there's the adjacent side, there's the opposite side and hypotenuse. So sine squared, right? Remember what sine is, that's opposite over hypotenuse. Plus cosine squared, which is the adjacent over the hypotenuse. Equals the hypotenuse squared, which is 1. This should be not hypotenuse. So we have two hypotenuses, right? So this is where it comes from. So this leads us then to sine squared plus cosine squared theta equals 1. And you'll see a little bit more of this when we talk about the unit circle in your next assignment there. But what's important about this identity is we could derive a lot of things from this identity. And I'll show you. For example, we could start off with sine squared plus cosine squared theta equals 1 and give us another identity. For example, we could go ahead and kind of morph this identity using some of the stuff that we do know already about the other trig ratios. Now think back to some of the things from the beginning of this video. Some of these other trig functions that we have. What we're going to look at is how we could get from this something like this. Tangent squared x plus 1, or we can use theta here because we use theta in the other one. This is another identity. Tangent squared theta plus 1 is secant squared theta. And we have cotangent squared theta plus 1 is cosecant squared theta. So where do we get these things from? Well, I'll show you. So if we start off with sine squared theta plus cosine squared theta equals 1, what if we divide everything by sine squared theta? So that'll cancel out to give you 1. Now, cosine over sine. Now, tangent of theta can be written as sine over cosine. And cotangent would be its reciprocal, right? So that would be cosine theta over sine theta. So it's all about like manipulation, right? Because technically that's where tangent really comes from. Tangent comes from taking the ratio of sine and dividing it by cosine. I just didn't show you that in the beginning because I didn't want to bore you with the details. But if we have cosine squared over sine squared, that gives us cotangent squared. And 1 over sine squared is going to be cosecant squared. Remember what I told you in the beginning, that cosecant theta is 1 over sine theta. Again, go back and review the video in the beginning and you'll see. So that's how we derive this one, you see. It's just that's out of different order. And if we start off again with sine squared theta plus cosine squared theta equals 1, how about this time we divide everything by cosine squared theta? So when we do that, sine squared over cosine squared, that's going to be tangent squared plus 1, because these will cancel out. And 1 over cosine squared is secant squared. So that's how we derive that formula there. So this is kind of getting a little bit ahead of ourselves, but just wanted to show you that, okay? Now, you have your assignment. What I'd like you to think about for next time is the following. I know we covered quite a bit here, but now you should be able to find ratios using the trig functions. You should be able to solve a right triangle completely. But I want you to think about the following. I want you to think of a table. Now we're just going to do sine, cosine, and tangent just to start. These 3 trig functions. And I want us to think about these special angles. 0 degrees, 30 degrees, 60 degrees. I should actually put 45 in between, I think. We'll put 60 there. And 90 degrees. So we're going to look at 0 degrees, 30 degrees, 45, 60, and 90. What would be good for us, people, is if we actually made a table to start off with these values. This will help you greatly going forward. So I know you have some spare time here now, but I know anything extra math you probably don't want to do. I was your age at one time. But this will be for your benefit, especially those people going to calc. See if you can fill this table in using the 45, 45, 90 triangle, the 30, 60, 90 triangle. See if you can fill this in. And then once you get sine, cosine, and tangent for all these guys, then the reciprocals are easy because you're just flip-flopping the fraction. And remember, if you have something like 0 over 1 as a ratio, when you flip it, it becomes 1 over 0, which now becomes undefined. So you are going to see some trig functions are undefined at certain degree measures, and that'll become more pronounced when we get into going beyond the first quadrant, and we go into the second quadrant, third, fourth, okay? So we covered a lot here. I hope this video helps some of you out there, though, that maybe still have a little bit of trouble. We're not done. There's going to be more to this. We're going to continue on with this, so continue the Khan Academy, and I'm going to continue making these videos to help you. I hope everybody's doing healthy and well. Kind of cloudy now. It was a little more sunny this morning. Get out and enjoy if you can for a little bit. Enjoy the rest of your day, and I'll see you guys shortly.